Is there an Earth-like planet in the distant Kuiper belt? The orbits of trans-Neptunian objects, TNOs, can indicate the existence of an undiscovered planet in the outer solar system. Here, we used N-body computer simulations to investigate the effects of a hypothetical Kuiper belt planet, KBP, on the orbital structure of TNOs in the distant Kuiper belt beyond about 50 astronomical units. We used observations to constrain model results, including the well-characterized Outer Solar System's Origin Survey, OSSOS. We determined that an Earth-like planet located on a distant and inclined orbit can explain three fundamental properties of the distant Kuiper belt: a prominent population of TNOs with orbits beyond Neptune's gravitational influence, and the existence of some extreme objects with peculiar orbits. Furthermore, the proposed KBP is compatible with the existence of identified giga-year stable TNOs in the 2 to 1, 5 to 2, 3 to 1, 4 to 1, 5 to 1, and 6 to 1 Neptunian mean motion resonances. These stable populations are often neglected in other studies. We predict the existence of an Earth-like planet and several TNOs on peculiar orbits in the outer solar system, which can serve as observationally testable signatures of the putative planet's perturbations. Part 1. Introduction. A trans-Neptunian object, TNO, is a member of the Kuiper belt located beyond Neptune with a semi-major axis of alpha greater than 30 astronomical units. These rock and ice bodies are the remnants of planet formation in the outer solar system. TNOs can reveal important information about the formation and dynamical evolution of the giant planets, such as their migration behavior and the fundamental properties of the protoplanetary disk from which they originated. More than 1,000 TNOs that belong to distinct dynamical classes have been discovered, allowing for important advances in our understanding of the trans-Neptunian region. However, a single evolutionary model that explains the entire TNO orbital structure has not been developed. Here, we focus on the distant Kuiper belt with alpha is 50 to 1500 astronomical units and discuss four main constraints that a successful model must explain for that region. 1. A prominent population of detached TNOs with orbits beyond Neptune's gravitational influence and not locked stably into Neptunian mean motion resonance, MMR. Typically, detached TNOs with perihelia Q greater than 40 astronomical units experience giga-year stable and non-scattering orbits within the scattered disk reservoir of the Kuiper belt. We used the orbital information on the AST-DYS observational database to determine that the apparent fraction of observed detached TNOs to the entire TNO population at alpha greater than 50 astronomical units is about 10%. However, the intrinsic fraction must be several times larger, as observational biases work against discovering more distant or large Q objects. Although estimations of the detached population can vary widely, they could be comparable to or larger than that of TNOs on orbits experiencing gravitational scattering by Neptune. Here, we assume that the intrinsic ratio of scattering and detached populations is less than or equal to 1 in the distant Kuiper belt. Oort cloud formation models, including galactic tides and passing stars, could generate only detached TNOs with at least alpha greater than a few hundred astronomical units. However, these scenarios are currently disfavored regarding Kuiper belt formation, thus they are excluded from our main discussions below. As considered in several representative models, including the favored Neptune grainy migration scenario, scattered TNOs experiencing MMR with coupled Kozai interactions or chaotic diffusion cannot explain the detached population, in particular, members with lower orbital inclinations. On the other hand, in the rogue planet scenario, the perturbations of a short-lived planet with 1 to 2 Earth masses during the early solar system could have produced a substantial population at alpha greater than 50 to 100 astronomical units. Here, we focus on producing the entire detached population with an appropriate intrinsic proportion to the scattering one as assumed above. 2. A statistically significant population of TNOs with high orbital inclinations not predicted by the Neptune migration, rogue planet, and several other outer solar system scenarios. The apparent fraction of high I TNOs within the observed population beyond 50 astronomical units is about 2%. These fractions become about 1% and 6% for the scattering and detached populations, respectively. Given the strong and observational biases against discovering high TNOs, e.g., most surveys focused on small or near ecliptic latitudes, the intrinsic population must represent a much more significant fraction. Here, we focus on producing the high I TNO population in the distant Kuiper belt by conservatively assuming that the intrinsic high I fraction is at least 2%. We also assume that this fraction should be at least 1% and 6% within the scattering and detached populations, respectively. In startling contrast, however, the above-mentioned representative models produce populations confined at I less than 45 to 50 degrees, with only an intrinsic about 1% belonging to the high I class. These results are in line with Kuiper et al., who claimed that models with external perturbations should be invoked to explain the high I population. Similarly, Gladman and Volk discussed scenarios to explain the existence of high I TNOs. Another intriguing feature is that scattering TNOs with I less than 50 degrees have been discovered in the distant Kuiper belt. It is unlikely that MMR and Kozai dynamics could generate these orbits because this mechanism predicts correlated high I and low E, large Q detached like orbits. Furthermore, the existence of some unstable TNOs with Q is 15 to 25 astronomical units, i.e., dynamically controlled by Uranus and Neptune, that possess I equals 47 to 169 degrees, implies that the inclination distribution tail could extend to about 170 degrees if high I TNOs are the main source of the reservoir of those objects. A high I reservoir in the distant Kuiper belt has been suggested in the literature. On the other hand, because other mechanisms could generate high I objects with Q less than 25 astronomical units, potential sources remain under debate. Summarizing, in addition to exploring the origin of high I TNOs beyond 50 astronomical units, we also investigated the possibility of a high I source reservoir in the distant Kuiper belt region. 3. A subpopulation of extreme TNOs with peculiar orbits difficult to obtain using representative models as discussed above. Extreme TNOs offer unique opportunities to better understand the outer solar system. For example, the discovery of 90377 Sedna and other TNOs with very large perihelia, greater than 60 astronomical units, revealed that the necessity to consider additional perturbations other than the four giant planets in the trans-Neptunian region. Here, we define objects with Q greater than 60 astronomical units, I greater than 60 degrees, Q greater than 50 astronomical units, and I greater than 50 degrees as extreme TNOs. In addition to Sedna, we identify 9 extreme TNOs. For specific assumptions during Oort cloud formation, e.g., dense stellar environments, passing stars may have produced TNOs on Sedna-like orbits. However, this scenario suffers from severe timing issues among other concerns. Alternatively, Sedna-like TNOs may be produced during dynamical interactions with a rogue planet. However, the short-lived rogue planet's perturbations imply the low efficiency of this process. More importantly, it is unclear whether all these models can produce the diversity of extreme TNOs as evinced here. For example, 2014 YX91 is an extreme TNO with a very high inclination and on a scattering orbit. Such a high I and low Q, high E orbit is unlikely to be produced by Kozai interactions during an MMR capture for objects interacting with Neptune because it instead produces high I, low E detached like orbits via conservation of the quantity cosine of I square root of 1 minus E squared. This behavior has been demonstrated in several investigations of Neptune migration and dynamics of individual TNOs. The very few objects with I greater than 50 degrees obtained in these models are outliers that belong to the detached population. However, the small perihelion of 2014 YX91 implies that this object is currently scattering. Furthermore, the inclinations of resonant dropouts and scattering populations obtained in representative models strongly concentrate within about 30 to 40 degrees. Therefore, considering these reasons, a hypothetical MMR capture coupled with Kozai interactions and subsequent resonance dropout is not a viable explanation for the peculiar orbit of 2014 YX91. Similarly, the orbits of other extreme TNOs are difficult to explain via resonant interactions during or after Neptune's migration. Therefore, a comprehensive model should explain the properties of a parent population, detached or high I, and the orbits of their extreme members. 4. A population of giga-year stable resonant TNOs in various Neptunian MMRs. This work defines objects that exhibit resonant libration for timescales longer than 1 gigayear as stable resonant TNOs. Conversely, the transient resonant populations established via resonance sticking are not an appropriate diagnosis of long-term dynamical stability, as they are scattering or detached objects temporarily captured in MMR. As demonstrated elsewhere and in this study, stable resonant TNOs have been found at 2 to 1, 5 to 2, 3 to 1, 4 to 1, 5 to 1, and 6 to 1, among other MMRs within 100 astronomical units. Most of these stable resonant TNOs remain locked in MMR for 4 gigayears, which suggests a primordial origin during the early solar system. There is sufficient discussion on the origin and preservation of these stable resonant populations within the framework of the representative Kuiper belt models. A successful model for the distant Kuiper belt should explain these constraints simultaneously. The model should also avoid overpopulating the orbital space at alpha less than 100 astronomical units with detached objects on small to moderate inclinations. Because although the probability of discovery is higher at small distances, observations have not confirmed a preference for lower I detached TNOs in this region. The representative models discussed above and other outer solar system models, considering 4 to 6 giant planet instability migration evolutions, have yet to demonstrate that they could satisfy all the main constraints consistently. In conclusion, the distant Kuiper belt probably did not form solely as a result of perturbation by the current 4 giant planets or hypothetical giant planets or rogue planets during or after the giant planets' migration. It is likely that a few thousand dwarf planets, objects with a mass comparable to Pluto or Eris, and several tens of sub-Earth and Earth-class planets formed in the outer solar system during planet formation. These bodies were mostly lost through gravitational scattering or collision with planets during their formation. Indeed, some models have considered the effects of rogue planets with masses comparable to Mars or Earth in the early solar system. However, these studies did not investigate the formation of the Kuiper belt. Thus, they only demonstrated that perturbations of rogue planets could lead to detached TNO orbits. On the other hand, the existence of a trans-Neptunian resident planet has been used to explain distinct properties of the Kuiper belt. Trujillo and Shepard proposed that a 2-15m planet located at 200 to 300 astronomical units is necessary to explain the alleged orbital angular alignments of TNOs located beyond 150 to 250 astronomical units. This proposal led to the Planet 9 model, which favors a 5 to 10m super-Earth planet on a distant orbit beyond about 400 astronomical units, with Q greater than 300 astronomical units. However, this model was not designed to explain the Kuiper belt's orbital structure, and many studies disfavor the validity of the alleged TNO's angular alignments. The super-Earth proposed by the Planet 9 model should not be confused with the sub-Earth to Earth-class hypothetical planets proposed in the literature and this study. Indeed, Planet 9 is much more massive and hypothesized to be located on more distant orbits. In addition, while Planet 9 was proposed to address possible peculiar properties of some distant TNOs, our scenario addresses the structure of the distant Kuiper belt by considering the above-mentioned constraints. Here, we consider the influence of Mars and Earth-class planets on the formation of the distant Kuiper belt. We refer to these planets as Kuiper belt planets, KBPs. Likovka and Mukai proposed that a sub-Earth KBP located at 150 to 250 astronomical units with Q greater than 80 astronomical units and I 20 to 40 degrees was required to explain the orbital structures and other properties of the entire trans-Neptunian region. Folk and Malhotra found that a KBP with a mass of up to 2.4 m, located within 100 astronomical units, could explain the plane of the Kuiper belt, but see Van Leerhoven et al. For a different conclusion. Early solar system interactions between the giant planets and several Mars and Earth class objects may have produced a resident planet within 200 astronomical units, with Q 40 to 70 astronomical units and I less than 30 degrees. Lakofka and Mukai demonstrated that a KBP could produce detached high I and transient resonant TNOs via resonance sticking, but at the same time effectively destroyed the stability of giga-year stable resonant TNOs depending on the KBP's mass and orbit. A stable resonant TNO may evolve for more than 1 giga-year timescales, protected against close gravitational encounters with Neptune. However, the gravitational perturbations of a KBP can disrupt this stability, so resonant escapees may acquire scattering or detached orbits. Because stable populations are well established in several resonances, the stability of the high eccentricity resonant members can constrain the perihelion of a KBP. Following this premise, Lakofka and Mukai found that any KBP must have Q greater than 80 astronomical units to preserve the stable populations in the 3 to 2, 2 to 1, and 5 to 2 MMRs identified at that time. The results of Lakofka and Mukai and this study rule out the existence of many hypothetical planets, including those proposed by Silsby and Tremaine. Similarly, observational constraints do not imply the presence of KBPs within alpha about 100 astronomical units.